Hi there, my name is Sterling Loza and I'm a PhD student in the Space Resources program. I'll be presenting on the effects of scattering on surface waves within the context of the NASA Mars InSight mission. This project is being undertaken with supervision from Ebru Bozdag, Associate Professor in the Geophysics Department here at Mines. And we're both currently working on this project as members of the InSight mission science team. So a little background first. InSight, which stands for Interior Exploration Using Seismic Investigations, Geodesy, and Heat Transport, launched on May 5th, 2018, successfully landed in the Elysian Planitia on November 2nd, and completing a roughly 300 million mile journey. And the aim of InSight is to determine the interior structure, composition, and thermal state of Mars, as well as constrain present-day seismicity and impact cratering rates. This kind of information is key to understanding the differentiation and subsequent thermal evolution of Mars, and thus the forces that shape the planet's surface geology and volatile processes. This is most often understood from a geophysical perspective, but from a space resources perspective, this type of information is also critical for future resource distribution probabilities and can lead to more efficient and targeted resource characterization and future prospecting efforts. Now, InSight is the first of its kind to explore the internal structure and dynamics of a solar system object on the Earth or Moon. And here we can see some major Marsquakes events that have been recorded and their distance and azimuth relative to InSight. Now keep that data point in mind because we're going to talk about it in a couple slides. Now as of September 30th, 2019, there have been 174 recorded seismic events with no impact-induced seismicity observed. This indicates a seismically active planet. And up top here, we can see the spectrogram for a single sol, which is what we call a Martian day. Now, the bottom image shows each day's spectrograms stacked on top of each other for sols 72 to 299. Now, the triangles represent low-frequency events, and the squares are high-frequency events, which mostly travel through the crust. There have been 24 low-frequency events and 150 high-frequency events. And this large, bright orange swath going through the middle represents periods of high noise, where the signal-to-noise ratio is effectively too low to distinctly determine P and S wave arrival times. Now, speaking of P and S wave arrival times, P waves are pressure waves and they travel the fastest, while S waves are shear waves and they travel a little bit slower. This is why P waves come before S wave in the graph. If we look at the waves in these graphs that we call seismograms. Seismograms simply show ground motion as a function of time. These four seismograms, specifically, displaying vertical displacement time series, show the similarities and differences of Marsquakes and earthquakes. You really need to understand this to understand why this work is important at all. And the top seismogram is one of the cleanest events in the Marsquake catalog and shows a high signal-to-noise ratio, which basically means we can really easily see the P and S wave arrival times. Now we can see the clear S wave in the top seismogram, which is the Marsquake that I pointed out earlier on the map. The second seismogram has a significantly lower signal-to-noise ratio, making it very difficult to determine the exact P and S wave arrival times, but we have other techniques for determining that. Now, notice how the earthquakes differ from the Marsquakes. In addition to the P and S waves, when we look at the third seismogram, we see a third category of wave, which we call surface waves. And these are distinctly lacking in the Martian seismograms, and that's the big problem. Now, the fourth seismogram here, which we can see is a pretty deep event relative to the shallow third event, also doesn't really show surface waves. This gives us the first of two possible explanations why surface waves are lacking in the Marsquakes. They could simply be too deep to really produce the surface waves, or at least those that we can detect. However, it is challenging to comment on these Marsquake steps with a single seismometer. So, the other way to tackle the issue of the missing surface waves, and the focus of this research, is by simply looking at the possibility of high scattering in the crust. So what is scattering? Scattering is caused by heterogeneities in a medium. A good example would be the Earth's crust. As waves travel across the crust through the crust, there are many regions, both big and small, that have different density and velocity profiles, like a pocket of oil located in a surrounding layer. Now, as the wave travels from one medium to another that has different density and velocity profiles, the wave reflects and refracts, which effectively scatters the wavefront. In the left, we can see the wavefront constantly being refracted and diffracted as it meets different perturbations in the crust. This is a highly divergent path from what would otherwise be a straight path, which would represent no scattering. In the figure on the right, which we're going to zoom in on, we can more clearly observe these effects on a seismogram. This shows 100 scatterers before and after a perturbation, and the waveform recorded before and after the perturbation at the receiver, which is the triangle in the graph, are shown on the right with the solid and dashed line respectively. As we can see, the non-perturbed solid line has a lower amplitude than the perturbed dashed line as we move to the right of the vertical bar in the seismogram. And these larger amplitudes signify strong and obvious scattering in the seismogram. And this trailing energy after the wavefront is what we call coda, and is how we observe scattering. We already have a comparative look at general seismograms for Mars and Earth, but let's complete the picture by comparing their scattering as well. On the left, we have the absorption along the x-axis and the diffusivity along the y-axis. And now we can see the moon events in the lower right-hand corner display strong scattering like terrestrial volcanic areas, which are the purple stars, with very low or virtually no dissipation. Dissipation on Mars, however, appears intermediate between Earth and the Moon, being quite comparable to those of crystalline massives, the blue stars. Martian scattering also has intermediate values of scattering between the Moon and the crystalline massives. Now, in the middle and on the right, we can see that the seismograms are somewhat similar between the two clear Martian seismograms and the terrestrial crystalline seismogram, which is the one on the bottom, but without the surface wave component. Now, relative to the Earth, the Moon and Martian seismograms exhibit quite a strong and very long coda. And the long coda on the Martian waves appear to be due to the interactions of teleseismic waves and with a heterogeneous crust. Now that we've covered these things, let's get into modeling. The goal of our project is to explore the absence of surface waves in the Martian seismic events with scattering. So effectively, we're looking at what kind of scattering regime we can have that would effectively kill the surface waves. To that end, we're going to use SpecFim 2D. And let me go ahead and, there we go. SpecFim 2D, an open source numerical solver to generate surface waves in layered media, add regular and random scatterers, and then begin altering the scattering properties, including things like strength and size, and of course randomly distributing them. Here we can see a homogeneous layer with material properties shown on the right. As the wave front propagates, it passes each of these two green dots, which is a receiver and produces a seismogram, which we see below. The seismograms here are the green dots in the red box, and the seismogram amplitude is the displacement in the x direction. There is no natural attenuations. The only thing that we should be seeing in the seismograms are the initial wavefront, reflections, and any scattering we might add. The left, bottom, and right sides of the model are absorbing boundaries, whereas the top layer is a free surface which does perfect reflection of the wave. And the source is a moment tensor explosion with a Gaussian source time function with the dominant source frequency of 10. Now, if we look at these seismograms, we can see the initial wavefront and the reflections, but there's not really any coda, which is good. That's what we're going for. Now, here we can see the effects of having a single small perturbation in the otherwise homogeneous layer. The scatter demonstrates 10% perturbation, which means that the S wave velocity is only 90% of the background layer. The other values are calculated accordingly. It's not too significant, so we only have one scatter here, but you can see the coda beginning to emerge in the seismogram. But it's pretty hard to see, so let's do a close-up. Now, here we can definitely see the effects of scattering beginning to take shape in the form of that developing coda, even though it's very small. Now we have numerous scatters in an offset fashion for a total of 17. And this coda is much more obvious from these seismograms, which again means that we're achieving the goal for this experiment. And given that the presence of the coda for these 17 scatters is so much more noticeable than a single scatter, it's easy to conceptually extrapolate from here on how we'd like to continue approaching these experiments and what we'd be aiming for. And just to make it completely explicit, what we're aiming for in these initial experiments are the presence of strong coda, which we can clearly see building up. Eventually, we're going to move on to actually using these techniques to try to reproduce the Martian data, which has no surface waves. And on that note, we're going to come to our future work. I'd like to add additional layers to the model to trap surface waves, continue complexifying the scattering regimes in terms of strength, size, distribution, and potentially other ways as well, like shape. Also, since scattering is different in 2D than 3D, I'm aiming to extend the experiments to 3D using SpecFim 3D Globe, also by the computational infrastructure for Geodynamics Group. It's an open source platform, open source software. It's quite robust and lends itself to the type of large scattering computing that I'll be doing. Thank you very much. I really appreciate it, and have a great day.